Okay, hello everyone. Today we're going to be solving another legal problem, which is 145. This is binary tree Postorder Traversal. The problem says, given the root of a binary tree, return the Postorder Traversal of its node values. So for example, let's look at example number one. Here we have this binary tree, and the output that we have to return is 3, 2, 1. But here, first sight, we cannot see how this is working. For the reason I already built this binary tree, it's the following one. So remember that for doing the binary tree post-order traversal, we start from the left, then we move to the right, and after that we move to the node. So let's get started. We start from the left. So the left child is 4. After we move on to 4, the other element we move to the right, so it's 5. Later we move to 2 because it's the node. And once that we're having that, again, we're gonna move to the right because it's the next element, which is 3. And finally, we move to the node, which is the parent, which is 1. So we have here the post-order traversal, which is going to be 4, 5, 2, 3, 1, because we have to visit all the nodes. This is something really important about sort of traversal. So something that I really like about doing post-order traversal is that I strongly believe that it's so similar to pre-order traversal. And actually the code as it's actually the same. It just with a few changes. So I'm gonna be starting here with the edge case. Remember that it is really important to have edge cases in case that our code didn't work well. For that reason, we're doing this because our recruiter can see that we have already strong knowledge about that structures and that we can see these cases in order that our code works from all the cases. So we're going to be starting when if root is none, it means that if we don't have anything, what we're going to return, okay, we are not going to return anything. So we're going to return an FP array later. Okay, so now we're going to be defining our stack. Remember that for that first search, the thing that we're doing is that we're using stack. For that reason, we can look through all the elements. So start, and we're going to be starting from the root, which is something that they're giving us to us. And later we're going to be having the result. So the result is going to be equal to an empty array. Now that we have that, let's get started. So while we still having elements in our stack, what we're going to be looking, okay, our current element is going to be equal to stack.pop. We'll be popping the last element that we're having in our stack. After we have already done that, we have to append that element to our result. So we're going to be appending that element to a result, which is result.append. And here we're having current.val. Once we're having that, here's when we have some similarities with the pre-order, but actually something really important is that here we're not appending. Here we're going to be inserting, insert this element in the 0 index and it will be current val. Okay, that's the first case because remember that when we're having our pre-order traversal, what we do is result.append and actually as I said it before, it's current.val. Okay, so that's the first like main difference because we'll be inserting all the elements in the 0 index. And we're going to be seeing how this works according to taking a test case. Okay, now that we're having that, we're going to be looking to current.left. Here we're going to be starting with the left, not with the right. And we're going to be adding that to our stack, which is stack.append. And then we're preparing our current element, which is going to be current.left. And if right element exists, so for example, if current.right exists, what we're going to be doing is stack.append. There we're going to be inserting the current.right. Okay, so once we're having that, it will loop well until we have elements in stack. And once that finish, we're going to be returning our result. So let's start. Let's run the code. As you can see, it's accepted, but I would like that you see how this is working. So, for example, if we're gonna be adding here our first element, which is gonna be our stack, and we're gonna be having in this line, we're gonna be having our result, right? So we're gonna be having here our result. Let's see how this works. So let's get started. First, we're in this line. So stack.root, we're gonna be adding the number one. So we're having here number one. And later, while stack, we have elements in your stack. That's correct. So we're gonna be popping the element. So goodbye one, and we're gonna be inserting that at zero index. So as we don't have any element here, we're gonna be having number one in zero index. Okay. So we're looking. So current left of our current element exists. Yeah, it exists. We're having a two. So we'll be adding that to our stack. Current right exists. Yeah, it exists. So we're going to be adding that element to our stack. Okay, so current stack pop. We're going to be popping three. We're going to be inserting three at zero index. So we're going to be inserting here in the zero index, and the number one, it's going to be in the next position. It has already moved on. Okay, so now we are looking from the tree. Current left exists? No, it doesn't exist. Current right exists? No, it doesn't exist. So we're going to be popping the next element, which is going to be two. And we're going to be adding that element at zero index. So, okay, we have already added two at zero index. And we have already moved all the other elements. Okay, so with two, current left exists. Okay, we're here in two. Left exists? Yeah, it exists. So added that to the stack. Current right exists? Yeah, current right exists. So add that to your stack. Okay, again, we still having elements in our stack. Yeah, we have elements in our stack. So stack.pop, we're going to be adding five at the beginning of our array. So current.left exists. Current.left, no, it doesn't exist. Current.right exists. No, we don't have any elements. So again, we see that we already have elements in our stack, which is four. So we're going to be popping that four, and we're going to be adding that to our results. So we have already inserted zero index. We don't have elements in right or left. So our stack is finally empty. So the final result we're going to be this one, which is already this array that we have already built. And as you can see, the result is the same as the Postorder Traversal that we have already done here. So we're going to be submitted our code. And as you can see, the code is accepted because we have success. As you can see, the runtime is actually great. If we're looking through the leetcode notation, we can see that according to memory, we have ON because we're using extra space because it is required. According to time, we're actually having ON time because it depends of the nodes that we're having in our root. Well, in this case, in our tree. So basically, that's all for this video, and I hope that you already understood the main idea of this concept.